In this video, we're going to discuss the conservation of momentum in the context of collisions between two objects. So I have some equations for you to look at right here. The first one applies to the collision between two objects in an isolated system. We can think of that as without outside influence, without an external force. We have mass 1 times velocity 1, which is the momentum of object 1, plus mass 2, velocity 2, which is the momentum of object 2. Together they equal the total momentum of the system prior to the collision, and they equal the total momentum of the system following the collision. And the apostrophe symbol on the V, which I'll call prime, represents final velocity for object 1 and object 2. So this statement mathematically says that the total momentum prior to the collision is equal to the total momentum after the collision in an isolated system. This statement holds for all collisions. There are specific types of collisions where other equations coexist with this one, and sometimes they're useful. So let's look at two other specific types of collisions. Elastic collisions are collisions in which not only is momentum conserved, but total kinetic energy is conserved, the energy of motion. Okay? And in such a case, the objects always move separately after the collision. This is a necessary condition, but is not sufficient. So, this still holds true for elastic collisions, but so does this. This also holds true for elastic collisions. This is a statement that says the total kinetic energy prior to the collision is equal to the total kinetic energy following the collision. And if these equations are solved simultaneously, you obtain this equality, which I'll discuss a little bit more later in the video. But it says that the difference between the two velocities initially is equal to the difference between the two velocities after the collision with a sign change. That's useful, and we'll observe that later on. Perfectly inelastic collisions are collisions in which the two objects stick together and move with a common velocity after colliding. So we have momentum of object 1 plus momentum of object 2. That's the total momentum of the system prior to the collision. After the collision, the objects are clumped together. There's one big mass moving with one speed or velocity. So we have mass 1 plus mass 2 times velocity prime. There's no subscript on the velocity because we're not distinguishing between objects 1 and 2 post-collision. They move with that same common velocity. In the real world, most collisions are not elastic or perfectly inelastic. So in the real world, we can use this equation as long as there's no outside influences, as long as it's an isolated system. But for the problems we're going to look at now, some are going to fall into the category of elastic, some will fall into the category of perfectly inelastic. So we can practice using these equations. We will begin looking at an example of each of these, a collision where it's neither elastic nor perfectly inelastic, and then one of these two, and practice using the equations. Okay, let's say we have an object. I'm going to represent objects with circles. You can think of it as a ball, although really these balls should be sliding, not rolling, sliding on a frictionless surface. So we have a ball or some object represented by a ball, that is 5 kilograms, and it is moving to the right at a speed or velocity of 3 meters per second, and it is about to strike a ball that is 6 kilograms, moving rightward at 1 meters per second. Once they collide, that will be the collision. After they collide, ball number 1, which was 5 kilograms, let's say it moves away at 0.5 meters per second. And ball number 2, which was 6 kilograms, it moves away at some unknown velocity, and we want to solve for that. That is a v2 prime. The prime symbol indicates that it is final velocity for object 2. So we use our master equation and we solve for v2 prime. We have m1v1 plus m2v2, total momentum prior to the collision, equals m1v1 prime plus m2v2 prime. That is 5 kilograms times 3 meters per second. You could probably do it faster in your head than I can write it out. Plus 6 kilograms times 1 meters per second equals 5 kilograms times 0.5 meters per second plus 6 kilograms times v2 prime. This is 15 kilogram meters per second plus 6 kilogram meters per second equals 2.5 kilogram meters per second plus 6.0 kilograms times v2 prime. I'm going to drop the units because they're getting tedious to write. We have a total momentum prior to the collision of 21. The momentum after the collision is also 21. Okay, it's also 21 in total. Over here we have 2.5 plus 6 v2 prime. And if you plug this into your calculator, you'll see that v2 prime equals 3.1 meters per second. Kinetic energy was not conserved in this case, but momentum was and always will be. Okay. Let's look at an elastic collision. Let's say we have an object 12 kilograms in mass moving 3 meters per second to the right. It strikes an object that is 4 kilograms moving rightward at 2 meters per second. It's going fast enough to catch up. A collision ensues. Afterwards, the 12 kilogram object is moving at 2.5 meters per second. What about the 4 kilogram object? Okay, we're going to use the same equation as before, and instead of writing it all out, notice that the momentum of object 1, 12 times 3 is 36. The momentum of object 2 is 8. So the momentum total prior to the collision is 44. Momentum after has to be 44 as well. 12 times 2.5, that's 30. And we add to it 4 v2 prime. I'm dropping the units, which makes me slightly nervous. But over here it's kilogram meters per second, kilogram meters per second, kilogram meters per second. The 4 is just kilograms. The meters per second comes from the velocity right here. 36 plus 8, that's 44. Subtract the 30 over 44 minus 30 gives us 14 remaining. 14 equals 4 V2 prime. So V2 prime is 3.5 meters per second. Now this was an elastic collision, and we said earlier that in elastic collisions, the difference between the velocities prior to the collision is equal to the difference between them after, with the sign change, because this is object 1 minus 2 and this is 2 minus 1. Okay, we could also write this is negative V1 prime minus V2 prime. The difference between the speeds here is 1. And look, it's also 1 here. Okay? That's confirmation that this is an elastic collision and total kinetic energy is conserved. This was elastic. Now let's look at an inelastic, perfectly inelastic collision. We're going to have a big object, 70 kilograms, moving rightward at 13 meters per second, hitting an object moving left at 5 meters per second. Second object is 50 kilograms. They collide, and this time they stick together. It's one big clump with a total mass of 120 kilograms. What is the velocity? I'm afraid to draw the arrow because is this thing going to go right or left? It's not immediately clear, and so I really shouldn't draw the arrow, so I'm just going to put a V prime here and we're going to solve for V prime. Although if you look at the numbers over here, there's a lot of rightward momentum and not as much leftward momentum. The total momentum is basically rightward, and so this does end up moving to the right. But we're going to show that. Momentum of object 1, 70 times 13 is 910 kilogram meters per second. Here we have 250, but this thing is moving leftward. The fact that it's moving leftward means we subtract 250. That's really important. Really, this is a negative 5 meters per second. That's a negative 5. Okay? It looks like this. 70 kilograms times 13 meters per second plus a 50 kilograms times a negative 5 meters per second. If we write it all out. Velocity has direction. Okay, and you might have thought I forgot to include the direction up here, for example, that I should have written rightward or east or whatever. But we're working in one dimension right now, and the direction is indicated by the sign, where positive is right and negative is left. So we have 910 minus 250 gives us a total momentum prior to the collision of 660. It's still 660 after the collision. After the collision, we have a mass of 120. Remember here we have m1 plus m2 times v prime from our formula. So that's a total mass of 70 plus 50, or 120, times v prime. So 660 equals 120 v prime. Running out of room here. So we have 660 kilogram meters per second equals 120 kilograms times v prime, and v prime equals 5.5 meters per second. So this entire blob, this entire object, is moving rightward at 5.5 meters per second. We know it's rightward because it's a positive number. That is a perfectly inelastic collision. We know that because the objects stick together. Okay. How about a colorful example? Look, a kid on a skateboard. Let's call him Matt. And a cat. Matt and a cat. You wouldn't believe how hard it was to find a cat image on the internet. I had to search and search to find a picture of a cat on the internet. It was crazy. But we have a Matt heading, let's say he's heading right at 5.3 meters per second. And Matt and his skateboard together weigh 40 kilograms. And the cat falls straight down onto the skateboard or onto Matt. And the cat has no horizontal velocity. Falls straight down. It's a collision of sorts. It is a perfectly inelastic collision because the objects stick together. And we want to find Matt's reduced speed after the cat lands on him. For momentum to be conserved, because the total mass of the moving object goes up, the velocity must go down. We have, as an equation, m1 v1 plus m2 v2 equals the sum of the masses at their new velocity for perfectly inelastic collisions. Here we have 40 kilograms times 5.3 meters per second plus the cat's mass, which I need to tell you, let's say that the cat is 4.2 kilograms. Okay, that's provided, that's given information. So the cat is 4.2 kilograms. What's the cat's velocity? Okay, this should be horizontal velocity. Matt is moving to the right at 5.3. We're focused on linear momentum along the x-axis, if you will. And it's only the cat's horizontal velocity that affects Matt's horizontal velocity. And the cat has 0 horizontal velocity because it falls straight down, because that's how I set up the problem. So this is 0 meters per second. The cat's horizontal momentum is 0 equals total mass of 44.2 kilograms times v prime, the final velocity. So we basically multiply 40 by 5.3 plus 0, has no effect, divide through by 44.2 to get v prime. So 40 times 5.3 is 212, so we have 212 kilogram meters per second, and that equals 44.2 kilograms times v prime, and v prime equals 4.8 meters per second, which you should check on your own calculator. So after the cat falls on Matt, he slows down to 4.8 meters per second, and momentum in the x direction along the x-axis is conserved. That's perfectly inelastic. Okay, now we have, what should we call him? Stan? How about Stan? Stan is standing at rest on an ice skating rink holding a bowling ball, which confuses the people around him. He and the ball are at rest. The total momentum is initially 0 for both objects. He throws the bowling ball forward, or leftward really, here. Okay? And we want to figure out how he moves after he throws the bowling ball forward. Let's say Stan is 73 kilograms and the ball is 6.8 kilograms. We're going to write out our master equation for momentum conservation. M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Prior to the action, it's not really a collision, he throws something from himself. Prior to the event, we have masses, but velocities are 0, so it's 0 plus 0. 0 momentum to begin with. So look, this side has to equal 0. So one of these terms has to be negative. So the bowling ball gets thrown leftward. It's going to have a negative momentum, a negative velocity and a negative momentum. Stan must recoil rightward and have a positive momentum in order for the total momentum to cancel and still be 0. So if the ball gets thrown at, let's say, 2.0 meters per second, then we have a ball of 6.8 kilograms with a velocity of negative 2.0 meters per second, negative because it's moving left, plus 73 kilograms for Stan at velocity v2 prime. What is Stan's velocity? How fast does he move to the right? How fast does he recoil, so to speak, to the right when he throws the ball to the left? Well, the ball's momentum is 13.6 to the left, so Stan's momentum must be 13.6 to the right. 13.6 divided by 73 gets us 0.186, basically 0.19. I'm not really worrying about significant figures, meters per second. So Stan moves rightward at that very small velocity. Okay. I'm now going to show you an interesting technique for solving elastic collision problems. So again, our master equation, M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Okay, this is going to be for elastic collisions. So in elastic collisions, kinetic energy is conserved. And we're going to make this a little bit more challenging by starting with only the initial velocities and figuring out both of the final velocities. Whereas before, I gave you one of the final velocities and we found the last one, which was pretty easy. Now we're going to start with only the initial velocities and find both of the final velocities. Okay? Here's the trick we're going to learn to solve problems like this. It involves the idea of center of mass. So the center of mass is a point that represents the average location for the total mass of a system. Okay, the average location for the total mass of a system. So here's the formula for calculating it, and then I'll draw a picture. the center of mass, let's say on a number line, and on an x-axis, the center of mass exists at point x. Okay, I mean, we would be solving for x. It would be a number somewhere on the number line. I'm going to write a cm for center of mass, and it's equal to, if there's two objects on the number line, we want to find the center of mass, which is some point between the two that represents a kind of average location of the mass, and it's calculated this way. So imagine that, we have a number line. And at point 3 on the number line, we have a mass of 20 kilograms. And then over here at 8 on the number line, we have a mass of 60 kilograms. So the center of mass, the average location for this mass, is not right in the middle of the two, but closer to the right one, because the righter one is heavier. And so we would say 20 kilograms times 3 plus 60 kilograms times 8 all over the total mass, m1 plus m2, which is 80 kilograms. And that is 60 plus 480 divided by 80, which is 6.75. So the center of mass is right here. It's a sort of weighted average. And based on the idea of center of mass, we are going to talk about the velocity of a center of mass. If these two balls are moving, if these are balls and they're moving, the center of mass will move in most cases. And we can calculate the speed or the velocity of that center of mass, which is not a physical object. There's nothing physically there. It's just a calculated point in space, and that calculated point will move as these balls move. And that's a useful idea for us. So we have the velocity of the center of mass, and it is equal to m1 v1 plus m2 v2 over m1 plus m2. Again, it's a sort of weighted average of the velocities. And this is a really useful idea. So, let's say that we have an object of 5.2 kilograms moving at 3 meters per second to the right, approaching an object of 3.5 kilograms moving at 2.0 meters per second to the left. So really that's a -2, right? Okay. We can calculate the total momentum here if we want. Actually, look, in the numerator right here is the total momentum. So there's a center of mass point in space somewhere between these two balls, and it's probably moving because the two balls are moving, and these balls are going to collide. They're not going to stick together. It's going to be an elastic collision, and after the collision they are going to move their separate ways, and we want to find both final speeds, and all we're given is this information right here. Okay, so both final speeds afterwards. Here's the two balls. Not sure what direction to draw the arrows. Are they both going to end up going right? Is this big one going to turn around? We'll find out. Let me label these. Okay, so why did we bother defining the velocity of the center of mass? And it's for this reason. We want to change our reference frame. So in our current reference frame, this ball is moving 3 meters per second to the right, and this one's 2 meters per second to the left. If we were running alongside this ball, then we would say its speed was now 0, and this one would appear to be moving at us at 5 meters per second. That would be a new reference frame, and we would have different velocities as measured in that new reference frame. We want to change our reference frame so that we don't have speeds of 3 and 2, because it allows us to solve problems like this relatively easily. So here's the thing. We subtract the center of mass velocity from each particle's initial velocity. Why? Because in that reference frame, that new reference frame, upon the collision, each particle's velocity reverses. So if it was 6, it becomes -6. If it was -3, it becomes +3. And then after we reverse the particle's velocities by changing the signs, we switch back to the original reference frame by adding the center of mass velocity to each velocity. Then we can state our answer in the same reference frame that the problem was stated in. So let's see how that works in practice, because that might have sounded complicated. We have, well, let's calculate the velocity of the center of mass. It's m1v1, that's 15.6, plus m2v2, that's 7, over the total mass, which is 8.7. I'm leaving off units, forgive me. Okay, this is 2.598. I want to include more digits than I really should, considering significant figures, so I don't get rounding errors. We'll round off at the end. So this is meters per second. So the center of mass, which is some calculated position in space between these two balls, is moving rightward at this speed as these balls move. We want to subtract this from both speeds. So for ball 1, it's going 3.0 meters per second. We subtract the 2.598 meters per second. And for ball number 2, it's going a -2 meters per second. And we subtract the 2.598 meters per second. And we get 0.402 meters per second and -4.598 meters per second. I'm sorry, you couldn't see that while I was saying it, could you? So these are the ball's speeds prior to the collision in this new reference frame. Now, upon collision, the cool thing about this reference frame is the speeds just reverse. Ball 1 now goes at -0.402, and ball 2 goes at +4.598. So number 1 is now at -0.402 after the collision, and number 2 is at +4.598 meters per second after the collision. So this is V1 prime in the center of mass frame, and this is V2 prime in the center of mass frame. Now, to change back to the original reference frame, we add back the center of mass velocity. So for number 1, we have a negative 0.402 meters per second, and we add back 2.598 meters per second. And for ball number 2, we're at 4.598 meters per second, and we add 2.598 meters per second, and we get 2.195 meters per second and 7.195 meters per second. And that's the answer. These are the two final speeds. This is now V1 prime and this is V2 prime, and it's our original reference frame, so it would be the answer that would be on the answer key, so to speak. And notice something. What's the difference between the speeds initially? The difference between a 3 and a negative 2 is 5. The difference between these two speeds? It's 5. So yes, it's an elastic collision. We only see that equality between the change in the speeds up here and down here for elastic collisions. So instead of going through all these steps, we're going to do the steps, but I'm going to show you a simplified way to do the steps. If you do all the steps, V1 prime ends up being 2 times the center of mass velocity minus V1, and V2 prime equals 2 times the center of mass velocity minus V2 prime. And remember, VCM is M1V1 plus M2V2 all over M1 plus M2. I could prove this to you. You could prove it to yourself pretty easily by doing those steps, but I don't want to waste time in this video. So, let's practice this. Let's say we have an object, 15 kilograms, 8 meters per second. It runs into another object. This is a big one, 50 kilograms, heading forward at 2.0 meters per second. They collide. What are the two final velocities? Well, the center of mass velocity is 8 times 15, that's 120, plus 50 times 2 is 100. So the total momentum is up on the numerator, and then in the denominator is the total mass, and that's 65. And this thing equals 3.38 meters per second. Now we double this and subtract V1 to get the final velocity of object 1. That's pretty easy, right? Double it, and you get 6.77 meters per second. So V1 prime is 6.77 minus 8. So that's a negative 1.23. And V2 prime equals 6.77 minus 2. So that's 4.77 meters per second. So we're done. Now this might sound complicated, but if you see the alternative, it would probably make you cry. So this is actually really nice. What's the difference between these two? 6. What's the difference between these two? It's 6. Okay, so that's a nice check. It's an elastic collision. This technique I'm showing you only works for elastic collisions. So here's our answers. Okay, look, ball number 1, it turned around. It's now heading left. It was a rebound. Ball number 2, still heading to the right, faster than it originally was moving. Whew, the video is 40 minutes long. I'm going to stop it. Hopefully it was helpful.